Hey everyone, in our last video we looked at central tendency, which was a fundamental question of how do we find the midpoint in our variable or in our data. We measured central tendency by either the mean, the arithmetic average of our values, the median, which is the midpoint in our values when they're rank ordered, or the mode, which is the most frequently occurring value in our data. In this video we're going to talk about dispersion, which is the second moment of distribution. Dispersion refers to how far away our observations are from that central value. So the three measures of dispersion we're going to talk about are range, interquartile range, and standard deviation. Range and interquartile range are fairly easy to understand. Range refers to the difference between the highest value and the lowest value. So the range covers the entire spectrum of values. So if our highest value were 100 and our lowest value were 60, we would have a range of 40. If we had a highest value of, let's say, 95, our lowest value was a 50, our range would be 45. If we were looking at income, and the highest income we had was, let's say, 150,000, the lowest income we had was 30,000, we'd have a range of 120,000. Interquartile range is similar to range, except that it discounts extreme high and low values. In this sense, interquartile range removes outliers from the calculation of the range. It's called interquartile range because it drops out the top quarter and the bottom quarter of our variable distribution. In the sense, the top 25% of high values and the top 25% of low values are cut out of the calculation, taking the high value from the 75th percentile and the low value from the 25th percentile and calculating that difference. Finally, we have standard deviation, which is the most complex measure we'll talk about, but also the most important for the rest of the things we'll do in this class. At its core, standard deviation refers to the average difference observations are from the mean. The concept, hopefully, is relatively straightforward. We're going to calculate the difference between each observation and the mean value, and then figure out, on average, how far all those observations are from the mean. Now, the calculation becomes slightly more complex because we're going to deal with the negative numbers using square roots and squares. Let's take a look at how we calculate all these values for our data.
Let's take a look at the range. Here I have the class average from our student data set. The range is simply the maximum value in our data set minus the minimum value. The range is appropriate for ordinal and continuous variables. Since ordinal and continuous variables can be rank ordered, step number one is to rank the values. Once we have the values ranked, we simply need to find the lowest and the highest value in our data set. Here you can see that our minimum value is 60, and our maximum value is 93. Once we've identified our minimum maximum value, we simply need to subtract the minimum value from the maximum value, which in this instance would yield 33. Alright, so let's take a look at how we calculate the interquartile range. The interquartile range is the Q3 value minus the Q1 value. Like the range, it's appropriate for ordinal and continuous variables. We begin the same way by rank ordering the variables. In step number 2, we're going to find the median value. Recall that the median is the n plus 1 divided by 2th value. In this case, since we have 25 observations, it's 25 plus 1 divided by 2. That gives us a median of the 13th value. I've labeled all of our values 1 through 25, and then you can see here that the 13th value is equal to 80. To solve for the Q1 and Q3 values, we simply have to take the median for each half of our data. So if we take the median for observations 1 through 13, we're once again going to take 13, add 1 for 14, and divide by 2. That gives us the 7th observation. So in this case, the Q1 value is equal to 75. To get the Q3 value, we have to find the median for the second half. We already know that the median of 13 is 7. So we treat the 13th observation as the first observation of the second half. We count up 7 observations: 13, 14, 15, 16, 17, 18, 19. So we know that the 19th value is the 7th observation of the second half, and therefore becomes our Q3 value. Once we've identified our Q3 and Q1 values, step number 5 is to subtract our Q1 value from our Q3 value to find our quartile range. So here we're going to subtract 75 from 85 to give us an interquartile range of 10. Finally, we're going to take a look at the standard deviation. Standard deviation refers to the average difference between observations and the mean. Note here that standard deviation is only appropriate for continuous variables. Students are often intimidated when they first see the formula for standard deviation. However, once you start unpacking what's under the square root sign, the formula hopefully will become very intuitive. You'll notice here that I have two different formulas. One is for a population and one is for a sample. The two formulae are almost equivalent, except that in the population we use the Greek letter mu to represent the mean, and in the sample use x bar. The other big difference is that in the population we divide by n, and in the sample we divide by n minus 1. The short reason for dividing by n minus 1 in the sample versus n in the population is that in the sample we actually don't know the parameter value of the mean. In other words, we don't know the real value of the mean in the population. So divided by n minus 1, we get closer to the true value of the standard deviation. You'll also notice that I use sigma to denote the standard deviation in the population and SD in the sample. Both are equally valid to use in your analyses. Let's take a look at the calculation for a sample, since we'll more often be using the sample calculation than the population calculation. Remember that the standard deviation as a concept is the average distance observations are from the mean. Let's start unpacking the formula and see how we actually measure average distance observations are from the mean using this calculation. If I want to figure out the average difference observations are from the mean, my first step is to calculate the difference of each observation from the mean. I can do this by doing what's in the parentheses of the formula. That is, I'm going to subtract the mean value from each one of my observations. Now intuitively, although we're not going to calculate it this way, we could figure out the average distance observations are from the mean by simply averaging the differences we just calculated in step 1. We could do this by using our average formula. That is, we could take the difference between xi and x bar, sum all those differences together, and divide by n. Let's take a look and see why that doesn't work with our average class grade data. Once again, our first step would be to take each one of the values of our average and subtract the mean. In this case, the mean is 79.48. The problem here is that if I subtract the mean from each one of the values and I sum those differences to divide by n, when I sum those values, I get 0. That is, the negative values, where the class average is lower than the mean, cancel out the positive values, where the class average was higher than the mean value. So the big reason we can't use our intuitive formula is that when we try to sum all of our differences, we end up with 0, which does not tell us anything about the variance or deviation around the mean. So the general solution with standard deviation is to square our differences to get rid of the negative numbers. And then at the very end, we're going to take the square root of the entire sum divided by n minus 1. Kind of the intuition here is that if you square a number and take the square root, you pretty much get back the same number. So if you take negative 2 and square it, you get 4. Take the square root of 4, you get back 2. So if you look at our intuitive formula and the formula for standard deviation, you'll notice that the only real difference here is, of course, that we're dividing by n minus 1 to account for the fact that we're dealing with a sample, and that we're squaring the differences and taking the square root. So let's just cross out the average and we'll kind of work off our square root formula. So once we have our differences from the mean, we can square each difference. After we square our differences, we can then sum the squared differences just like we would in a regular mean calculation. Adding together our squared differences, we get a sum of 1,478.24. Just like we would do with the mean, where we take our sum and divide by n, we're going to divide this by n minus 1. 25 minus 1 is 24. Dividing 1,478.24 by 24 gives us 61.59. The final step is to then take the square root of that value. So taking the square root of 61.59 gives us a standard deviation calculation of 7.85. We know then from our calculations that the average of students' final grades is a 79.48 with a standard deviation of 7.85. This means that our general expectation is that a student is going to finish, on average, with an 80% in the class. We also know that with the standard deviation that most students in the class will finish somewhere between around a 71 and an 87. Standard deviation is highly useful because it allows us to compare different cases that have similar means but perhaps different standard deviations. So imagine we had a second class where they had the same mean score of 79.48 but a standard deviation of 12.5. In the second class, the standard deviation tells us that the students are more spread out around that mean. So whereas we expected the majority of students in our first class to generally finish between a 71 and an 87, in our second class we would expect that students would finish somewhere between a 67 and a 92. Finally, imagine that we had a third class with the same average of a 79.48, but this time we had a standard deviation that was much smaller at a 2.37. Here, we'd still expect students to finish with about an 80 average, but we'd expect that most students are going to finish much closer to that average. On the low end, we figured that the majority of students would finish somewhere around a 77, and at the high end, we'd finish that most students would finish around an 82. So in this video, we talked about dispersion, or really variance in our data. The range told us the maximum dispersion. That is, the range is simply the difference between the highest and lowest value. The interquartile range is calculated similar to the range, but it discounts the top 25% of values and the bottom 25% of values. Finally, standard deviation measures the average distance observations are from the mean. Standard deviation is a useful metric by which we compare the variance or performance of different cases that have similar central tendencies or midpoints. Standard deviation is a critical concept for a lot of statistics we'll look at in the rest of this course. If you need to revisit standard deviation, please come back to this video and look it over a couple times to make sure you understand perhaps not so much the mathematical formula, but the conceptual meaning of what the measure is trying to capture.